Thank you. Thank you for the introduction. Yes, I have to click the button. Okay, yes. So this is the third talk. As I promised, I'm going to discuss specific cases, namely the mapping class group and the relatively hyperbolic groups. So the talk will have some overlap with Abdul's talk, but I'll go more slowly and try to give some details and maybe tell you guys where the P thing came from also. So yes, as usual, please feel free to interrupt. And if there are questions in the chat, somebody should read them to me, and I'll be happy to answer. Okay, so right. So the sublinearly Morse boundary, as we discussed, picks out the hyperbolic directions in a space, right? So it's a generalization of a Gromov hyperbolic. It's the setting that we start from is the Gromov hyperbolic spaces. But now we want to think about spaces which kind of are not Gromov hyperbolic, but they do have some hyperbolicity. So one good example of that is this relative hyperbolic groups. So I want to, since for a graduate student, maybe they've never seen this before, so I want to talk about that a little bit to motivate. So, I mean, the motivation for all of this is kind of H2 and the hyperbolic surfaces. And you can also think about the hyperbolic manifolds, right? So hyperbolic manifolds are the quotients of the three-dimensional hyperbolic space by some group, this co-compact. But there's this other kind of more interesting class of hyperbolic three manifolds, which are not co-compact quotients of H3, but they have finite volume, right? So let's say M be a hyperbolic three manifold. Finite volume. So how does this look like? It's kind of hard to draw a hyperbolic three manifold, so I kind of draw it schematically. They have some compact part which has some topology. So it's not clear how to draw topology, right? But they also potentially have some a number of cusps like that. But the cusps in the two-dimension are just circle cross rays, right? Since this is a three-dimensional space, the cross sections are two-dimensional, but they have to necessarily, if you want this to be a finite volume, you necessarily in this case have to be tori. Right? So the ends of these guys are tori. So this is M, right? So if you think of this as a model for the fundamental group of this, then the fundamental group of M is not hyperbolic. So why is that? Because you have this tori in the boundary. So if I pick this torus like T, then the fundamental group of the torus kind of embeds inside of the fundamental group of M, right? And this is just a Z2. So you have Z2 fits inside of this in an undistorted way. So they have flats, and flats are opposite of hyperbolic, right? So if you have a flat, the triangles are not thin, the projections are not contracting, and so on. So there are like flats sitting inside of this group. So this is not really hyperbolic, but somehow this picture still tells you something, right? There is some hyperbolicity inside of this group. Means that if I just cusp these guys off, if I just somehow make them by hand be on, instead of being undistorted, make them be distorted, then the group does become hyperbolic, right? So you kind of feel like if I look at the group and I look at these flats and I cone them off, then the group becomes hyperbolic, right? So that's exactly what you want to do. So let's look at maybe the universal cover of this, because that's kind of a better model for the group. So if I look at the universal cover, and maybe I could make this torus be green, this torus be red, right? So this green guy kind of lifts to some kind of a, it's a copy of R2, but it's distorted, so it's kind of like a boundary of a horoball. So it basically becomes some two-dimensional porosphere here. and the red one kind of like that. And there are, of course, many copies of each one of these guys. Right? Up to conjugation, so you have a bunch of these things like that, and then of different sizes, and there are other ones, right? So there are flats in the group, but they have been killed off, so like they have only one point at infinity in this H3, right? So, and if you do that, then the object we get is hyperbolic. So the key thing is like you have a group which is kind of like basically the same as this H3. You have some flat subgroups of it, right? And then you want to kill these guys off. But for the whole thing to be hyperbolic, the important thing is that this green one and the red one, they don't fellow travel each other for a long time. I'm not killing off things which are kind of parallel for a long time. A green one and a red one comes close for maybe a tiny bit, right? But then they wear off. And then maybe there's another copy of the green one over here. And these guys maybe spend some small amount of time close to each other, but not so much, right? So this picture is very beautiful. Like you want to think of this group as a hyperbolic group, or kind of like essentially a hyperbolic group, but this is of course not. And you want to say, okay, so there are these Z2s, but except for these Z2s, the group is hyperbolic, right? So we want to make this notion kind of more precise, and this is where the notion of relative hyperbolicity has come up. So maybe I have some space over here. So let's say you have a G is like a finitely generated group. And then you have like a bunch of tori, right? So each of them give you a subgroup. So let's say P1 to PK are some subgroups. We call them the peripheral subgroups. Right? So and what I want to do is I want to pick this group Pi, and all its conjugates, and I want to kill them off. So there are several ways to kill them off. You can physically attach like a cone into them. Like, so you look at your group, and then there's this flat inside of it. So you can attach like a copy of an upper half plane horoball, like a horoball to this to cone it off. That's kind of like something that was favored by Gromov, I think. Another way to do it is you pick a point and attach it to everybody else. So the whole thing has finite diameter. So that's the Benson Farb. But let's, yeah, maybe I'll just write some names here. So yeah, I mean, but the notation I'm going to use is kind of is used by Sisto. So the other way is like basically pick any two a vertex inside of this P group and add the edge between them. So we don't need this extra edge. This extra edge is kind of like not part of the group, so it's kind of like causes some problem. If you don't want to do that, you can just attach an edge between any two elements. So the option of all this is either this becomes logarithmically distorted or just becomes diameter 1, right? So we just do the diameter 1. So you're just killing off all these guys. So I can define so G, when I say G, I mean, think of it as a K graph of the G, and look at the G hat to be the same as G plus an edge connecting every two elements, X and Y, that are in some coset of Pi. So if I pick a Pi and I conjugate it to somewhere else and pick any 2 points in here, I connect them by an edge. So the upshot is that the diameter of the Pi's become 1 instead of G. So from this K graph of the group G, I can produce this other graph, G hat, which is quotient off. And we would say that the G is relatively hyperbolic if two conditions are correct, which means the G hat is hyperbolic. And the conjugates of this PIs are not so close to each other, right? I'm going to write this vaguely. The correct definition is kind of like something like this, that every edge that you pick lies on finitely many cycles of size n or something. So there's some fineness condition, or there's this thing called the bounded coastal penetration. So maybe I'll just write that. Okay, so it just means that these four balls don't float out each other for a very long time, right? So this is the picture you should have in mind. Okay,
Hi, Kasra.
Yes.
Is Sisto's construction the same as just throwing all the non-trivial elements of the piece into your generating set and taking a k-graph?
That's right. That's correct. So it kind of becomes an infinitely generated set. That's correct. Okay. Any other question? So right. So this is a good example for us because the group is not hyperbolic, but has a lot of hyperbolicity in it. Right. There's this underlying structure that the way that these PIs are glued to each other is hyperbolic, even though each of these PI necessarily is not hyperbolic. So we want to see if what are the hyperbolic directions in this kind of space? Yeah, let me see if there's anything else I want to say. Okay, so what are the properties of, just recall some properties of relative hyperbolic groups. So yeah, basically, like, what do geodesics look like? Right. So, I mean, I want to describe a model for this geodesics, which gives you basically a quasi-geodesics, right? So I always have G and I have G hat. As a vertex set, these guys are identical, right? And I can pick 2 points in X and Y, and then let's say I want to connect them to each other. So one thing I can do is I can look at them as elements of G hat, and I can connect them here by geodesics. And then I try to like bring this geodesic back over here to produce something, right? So the picture that you should have is as follows. Let's say I have a point X here and a point Y, right? And I want to connect them in G hat. So in G hat, going through peripheral subgroups costs you basically nothing, or cost you 1. So just imagine that from point of view of the P1, the projection of X and Y are very different, right? So I'll draw this picture over here. So pick a peripheral subgroup P and pick X and Y. And imagine that the projections of X and Y into P are far away from each other. So this is long. So the hyperbolicity of this G hat, kind of what it does for you, says that the geodesic connecting X to Y basically has to come to P to use this shortcut and to go away afterwards. So if you're staying far away from P, that is not an efficient path, right? So there are many different ways to say that, right? But this is the basic picture. It's like this part, so let's say I want to go from X to Y. So I can project X and Y into here, right? So let's call this X P1 and Y P1. And I have some X P2, Y P2, X P3, Y P3. Right, these are the closest projections of X and Y to these PIs. And these are the ones, let's say, that the projections are kind of far away from each other. Right? So in fact, these guys happen to line up inside of G, right? And the geodesic kind of looks like this. You go from X to G, to XP1, you connect to YP1, then you go to the XP2, you connect here, and you go like that. So this is kind of a good model for a geodesic, right? So this is a quasi-geodesic. You basically have to do that. And in fact, if you look at the actual geodesic, it may not go exactly along this P, right? Because I mean, here you can just go parallel and be equally efficient if you're moving in G, but the real geodesic kind of stays in a small neighborhood of this guy. Well, small means like a big number, but it's still small compared with the, so there's like some particular D that this geodesic has to actually enter here. So the real geodesic doesn't do something that is so far away. So this is a geodesic in G. And these PIs are basically the geodesic in G hat. So there is a kind of a close relation between the geodesic here and here. So if I pick a geodesic in here, I can always lift it to a quasi-geodesic over here, right? So maybe I write some of these.
Kasra?
Yes.
How nice is this quasi-geodesic you produce in G? Like
all uniform constants?
Not just uniform constants, but is it anything like hierarchy path or?
Yeah, this is exactly like hierarchy paths, right? Yeah, it's exactly right. So yeah, I mean the relative hyperbolic groups have a lot in common with this hierarchy hyperbolic groups, right? So or with mapping class group, but it doesn't fit. Like the mapping class group is not relative hyperbolic, right? So yeah, in some sense this is kind of a stronger condition, but the setup is a little bit different. Yeah, but the arguments often are the same or similar arguments work in both of them. And in this particular case, the same arguments exactly work in both mapping class group and the hyperbolic group. And if it works in mapping class group, so of course works in other HHG groups also. Yeah, so right. So you should think, for people who know, you should think of this as a hierarchy path. So hierarchy path is something like that is moving like a quasi-geodesic, like moving forward with no backtracking in G hat, and in each of the PIs is also going forward. So it's efficient from point of view of all the elements that we're considering, right? So I mean, potentially you could do something and undo it and then do craziness, but yeah, these are good quasi-geodesics. Okay, so geodesics in G hat lift to quasi-geodesics G, so that's one thing. Or we can say if the distance in some peripheral subgroup P of a projection of X to P and projection of Y to P is large, so for some L, then the geodesic segment XY in G intersects a D neighborhood of this segment XP, YP in G. So more than intersect, it actually comes kind of close to the beginning of the projection and leaves close to the end of the projection. So basically all the strong sentences like that you want are satisfied. So maybe I write one more. There is also what is called a bounded, this is the third property, projection image theorem. This is a theorem the first proven by Mazur and Minsky. For the mapping class group. But so it turns out to be extremely useful. So what does that say? So let's say you have a peripheral subgroup P and you have some points X and Y, right? You can look at this picture in G hat where all the P's are killed off. And this space is hyperbolic, right? And now you have some X and Y. And let's say this P is nowhere near this segment, right? So imagine that this P is nowhere near this segment. Then the geodesic connecting X to Y doesn't come to this at all, right? So so that's kind of what we were saying here. And in fact, better yet, the projection of X and Y, I mean, this is the hyperbolicity of G hat kind of kicks in. like if X and Y are closer to each other in the G hat sense that they are to P, right? As I project them to P here, the hypervelocity of G hat kind of kicks in and bring these guys together. So the projections of X and Y to P are bounded distance from each other, right? So yeah, you can write it this way, you can write the contrapositive. If dP xy is large, then P is near the geodesic xy as the geodesic in G hat. The P has to be near. So, right, you write it this way and say bounded projection image theory, but this way there is no bounded projection, right? But the contrapositive is bound projection. If P is nowhere near this, then the projection is bound. So if I have a projection, I have to come close. So yeah, the sentences like that are kind of correct. I hope you get, like, the union of these sentences will give you a picture of what the space looks like, right? So the space is not hyperbolic, but you can use this hyperbolicity all the time to produce outcomes that are good for you. Okay, any question about the definition of the relative hyperbolic group or its properties? Okay, so good. So we want to, let's say you have a geodesic in this space and you want to prove it's sublinearly Morse. How would you go about it? In fact, that's what we want to do, and in fact, that's what Giulio is going to do, right? So what it turns out to be the case is that if you have a geodesic produced by, like approximating tracking a random walk trajectory, it will be very special, right? So the random walk trajectory is kind of, don't spend too much time near a particular peripheral subgroups, right? So Giulio will talk about all that, right? So you should think of this. So why is that true, right? Like if I draw this hyperbolic picture, it becomes kind of more clear. Let's say you're randomly walking inside a hyperbolic 3 manifold, right? And you have all these horrorballs. So there are two things you can do. You can either kind of like walk along here, or you can jump to the next one. Then you can walk along here, then you can jump to the next one, right? So this is kind of a random walk and how it looks like. You just kind of walk along some horrible and you jump to the next horrible. If you're doing this randomly, you're not going to do the same thing over and over again, right? So the probability of having a bunch of heads in a row is very low. So you might walk a little bit along here, but eventually you'll jump to the next one. And then when you walk along here, you're not going to jump back to that. You're completely far away from that. You're going to jump somewhere else. So you're going to go to infinity. And the amount of time you spend here is kind of bounded, right? Well, it's not bounded. If I have a sequence of heads and tails, you don't expect to have only one head at a time. It's not going to flip over, right? So by luck, you will have some long sequence of heads. But the length of sequence of heads are growing kind of sublinearly, in particular logarithmically, right? So if I have the same way that I have a sequence of heads and tails, you expect to have some long sequence of heads, right? But if you flip the coin n times, the longest sequence of heads you have, you expect it to be logarithmic. So the same way, if you're moving in this relative hyperbolic space, you expect to spend only logarithmic amount of time near each particular peripheral group, right? Okay, so I'm not going to get too much into that, as Giulio will. Right. So, but the outcome of this is that if you try to find some geodesics that track a particular random walk, they have this kind of property, right? What did we call them? Yeah, we call them I forgot. Like kappa excursion. Yes.
Can you say a little bit about what are you assuming of the peripheral groups?
What do you mean?
If anything, like, are they
flats or something, you mean? No,
are they flat or non-positively curved or hierarchically hyperbolic?
No, I'm not assuming anything. No, the peripheral subgroups can be absolutely anything. I mean, yeah, it doesn't matter. I mean, the thing is, yeah, you're right. I mean, it's possible that the flats themselves have some hyperbolicity, right? So it's possible for a sublinearly Morse geodesic to spend all of its time in one of these peripheral subgroups. So I'm not saying that's not possible, right? But I'm saying if you're doing a random walk, even though those guys are sublinearly Morse directions, the random walk will not follow them, right? The random walks jump from peripheral to peripheral. So really what they do is they move forward in G hat, right? So it's possible in the process of going to the G hat, you have killed off too much hyperbolicity. So yeah, so in some sense, random walks are really, really special, like way more special than sublinear Morse guys, right? Way more special. There could be some hyperbolicity inside of these PIs, but still you don't do that. You jump off from peripheral to the next person. Right, but anyway, so I want to give this property a name. So I would say, so let's say gamma is a geodesic ray. So I would say gamma has kappa excursion. If this exact thing happens, yeah, how am I going to write that? Yeah, let me do it this way. So if for every P, I write some fancy P. So this is a space of all left cosets of all the peripheral subgroups, right? So let's say if I have some P, and here's the origin, and then gamma is coming, right? So it's possible, so I can pick some neighborhood of this. It's possible that the gamma comes close to that, I spend some time in here and goes away. Right? So if you're kind of spending a lot of time near P, it's the same as kind of being in P. I don't make any difference between it, right? So I want to say the length of gamma intersect D neighborhood of P. So D is, maybe I should call it D0, is some fixed uniform constant. So this is bounded by kappa of norm of P, basically, in G hat. The norm P G hat, it's kind of the usual thing, is a distance from the origin to P in G hat. And this makes sense because P in G hat has diameter 1. So just the shortest, the closest one. Okay, so right. So basically, the picture is like this, that you kind of come to different peripheral subgroups and you spend different time. And if you're on the nth peripheral subgroup, I want the amount of time that you spend next to it to be less than kappa of n. So the length of this segment, I want to be less than kappa of n. So this is somewhat a strong, as Ulam mentioned, it's kind of a strong assumption here, right? This is by no means equivalent to being sublinearly Morse, right? But I want to say this implies sublinearly Morse. Right? So these are the guys that appear in the random walks. So our goal for today is to show that this kappa excursion implies. And in fact, the path to do that is to prove that it's in fact kappa contracting. Which implies kappa. So the reason I picked this particular example is because this kappa contracting sounded a bit weird to begin with. First of all, they had this kappa projection maps. And then you're like, why? I mean, I'm sure in the back of your head, you're like, why can't you just take the closest point projection? I know it's not QI invariant, but it's a nice thing. It does the job. Why do you have to like talk about this weird projection? So then just remember what kappa contract, I want to remind you what that was. And I'm going to see like why these guys kind of appear naturally, right? So you have to deal with them. It's not only that this is the minimum you need to prove that, it's that also these guys appear naturally. So often you have projections which are just kappa contract. That's all you know about them, right? And then the closed projection doesn't really do the job. You need some other kind of projection. Okay. So this is what I'm going to do. So recall, I don't have to define kappa of Morse today because all we have to do now the kappa contracting implies kappa Morse, and we're already going to prove the contracting one. So I would say a set Z sitting inside of X is kappa contracting. Can you guys see all the way to the end? That's readable, right? I think it's covered by the. Okay, so if there exists a map pi from Z to X, so I want pi to be from Z to X, from X to Z. I want pi to be a kappa projection. So what does kappa projection means? It means this picture. If I pick a point Z in here, pick a point X in here, and I look at the projection of X, right? So I want the distance between, so for Z in Z and X in X, I want the distance between Z and the projection of X to be bounded by some number C1 times distance between X and Z plus C2 kappa of normal X. So up to error term of kappa, the map is Lipschitz as far as the points from here to here are concerned. Right? So the projection is distance non-increasing up to kappa error term. Very, very weak notion of projection. Right? So you need a kappa projection such that the following thing is true. So there is C1, C2, D1, D2. This is C1 and C2, such that if the distance between X and Y is less than or equal to D1 distance between X and Z, then the distance between projection of X and projection of Y is less than 2 times kappa of normal X. So contracting meaning the balls that are disjoint, but like way disjoint, right? So I want this to be much, much smaller than that. Then the projection of the whole thing has a kappa of X and right. So here Z is going to be this set gamma, right? And the question is, what is the projection map? Okay. So let's talk about why the closest point projection is not so good. So, I mean, maybe, first of all, the closest point projection kind of depends on the generating set. If you change your generating set, things kind of go crazy. For example of how crazy things can go under, you should look at maybe my paper with Yvonne Verber. Should we do this in some open class group settings? So when you have like the axe of a Sudanosov, and we show that it's not contracting, right? So, right, the thing is, so you really have no control what the closest point projection is. But even further, like let's say you kind of did, like you said, say this is some peripheral subgroup P, which is basically a flat. So just imagine you have some generating set here, which has like 3 generators. So kind of the Cayley graph looks like some kind of a triangulation like that, right? So here's your gamma, and let's say your gamma is very, very nice. It comes in here, exits over here. So this is gamma. And let's say you have X somewhere else, and the X projects closest to P is over here. So since there are these flats kind of in your space, the question is what this should be the closest point projection from this XP to the gamma. Well, you can go along the Cayley graph along any path here. You know, all these guys are geodesic. They have exactly the same length. So this whole segment here is the same distance from this point XP, right? And our space was kind of, okay, had kappa excursion. So the amount of time you spend in P is bounded by some kappa of something, right? So even everything is perfect and you understand everything carefully, there is no way you could pick any of these points, right, as a favorable point to some other one. So the projection is never going to be well defined. If I go about projection of the balls, the projection of just one point is never going to be well defined, right? So yeah, I mean, so really I have no choice but to add these error terms to it. So yeah. And further, you have no control what the cross projection does anyway. Like really what we want to do is you want to do the closest point projection in some hyperbolic space, because hyperbolic spaces have thin triangles and the projection there kind of makes sense, right? It's kind of like a geometric thing. If you change your generating set or whatever, the G hat just changes, you know, a little bit. Like things move like, you know, the geodesics go to quasi-geodesics in G hat, but they stay bounded distance from it. Like if I, yeah, let me just say that kind of more slowly. Let's say I have G hat with some generating set and I change the generating set. So now I have a different G hat, but the two G hats are quasi-isomorphic to each other. So what was a geodesic in G hat before becomes a quasi-geodesic. But the projection of X to a geodesic or the quasi, these are all the same. So the error term here is always bounded, even if I change my generating set, right? So this is a robust concept. The projection in G hat is a robust concept. The projection, the closest projection in G is not. That depends on it's too wobbly. Right? Too wobbly. So really you want to do this. You want to say, okay, let's project X to here. But what is here? This is a bounded distance. So there's a bunch of PIs here, right? So you don't know which one of them to pick. And each of them have a segment which is kappa long. You don't know which one of those to pick. So you pick all of them. You pick all of them, right? And you're happy. And then you prove that the diameter of what you have projected is kind of still bounded by a kappa. And so you have a kappa. You don't have a real projection, but you have a kappa projection, right? And life goes on. Okay, so let's make this a bit more precise. Is the heuristic clear? I hope it is. Right, so that's what I'm going to do. Yeah, I forgot to write one property of the relative hyperbolic groups. So maybe I'll do that and then So the relative hyperbolic groups, kind of like Markov group, they have a similar distance formula, right? And this is what we're going to use to bound distances in G. So the picture again is as usual, is like that. So if I pick, I'm drawing the same picture because that's the picture that you have. And there are many sentences describing this picture, right? The picture is that this is a good quasi-geodesic between X and Y. Right? And these PIs form a geodesic in G hat. This is the picture. So one more consequence of this picture is that the distance between X and Y is basically sum of the distance of projections in each of these PIs. Right? Okay. The problem is if I pick a PI, which is kind of a completely somewhere else, these guys will still have some non-zero distance between them. So I don't want to do that. I want to pick all the big ones. The problem is if I pick all the big ones, then they could be all less than that. So they could be zero. So I have to just also count how many of them are and how many of them are big ones and add them up. So for every X and Y in G, the distance in G between X and Y is equal to, this is up to some multiplicative error, the distance between x and y in g hat. So that's the number of these peripheral subgroups that appear, plus for the large ones, you should look at the distance in this peripheral subgroup between the projections of x and y in here. Okay, to say the large ones, I put a floor k. This is a function which is 0 if x is less than k, and just x if x is bigger than equal to k. So again, the standard notation for people who know the distance formula in mapping class group, all this was introduced by Mazer and Minsky, but they work the same way for relative hyperbolic groups. Okay, so basically, if I want to say 2 points are close in G, that's my main tool. I'm going to say that they're close in G hat, and I'm going to see how many different peripheral subgroups are relevant here between these two guys, and I find all the large projections and I add all those guys up. Right? Okay.
Kasra, can I ask a question, please?
Sure.
So because you were about to erase the right-hand side, I was stuck on something. So
yeah,
I thought kappa projections implied immediately that the distance between a point and the nearest point projection is coarsely up to kappa within the distance between the point and the kappa.
Unfortunately not. It's linear. It's not kappa, right?
No. The distance.
This is x.
Between, yeah.
Let's say this is x z. This is the closest point projection.
Yeah.
And the kappa projection. This distance could be linear to that.
No, I don't mean the distance between the points. I meant the distance between x and pi and the kappa projection of x and the nearest point projection of x.
This distance, right?
No.
This is the nearest point projection. This is the kappa projection.
No, I meant the distance between x and pi of x.
Yeah.
X and the nearest point projection.
Yeah.
And the distance between x and.
Yeah, these guys are comparable linearly also. Yeah. Right. I mean, so let's say.
Yeah. So
this distance is like dr plus kappa, which means this distance is d plus 1r plus kappa at most. Yeah, it could be linearly far away.
Yeah. Okay. So you can bound the distance between x and its nearest point projection by the above by the distance between. Yeah. Okay. Never mind.
Yeah, you can. Yeah.
Okay.
So if this is d plus 1, if you want to find this, then if you know this one, you can add another linear factor and find the other one. Yeah. So it's all linear. That's correct. Yeah. So this distance is linear to that. So the length of these two guys are linearly comparable to each other. Yeah.
Thank you.
Up to some kappa. Yeah, that's correct. Yeah. Again, it looks weak. It's weird that it has any consequences, but it does. Okay. Anything else? Right. So we're going to define a map that has this property. So I'm going to define this pi projection, and I'm going to be like as generous as possible. So the projection maps are not just one point. You can have them be sets if you want. If you don't like, you can pick a point in those sets. So it's kind of up to you. So, and I want to pick the largest possible set, like any point that could reasonably be counted as a projection of x to z or x to gamma, right? Okay, so let's say gamma has this kappa excursion. Gamma is a ray. Kappa excursion, so that's the picture of that, right? So, and I define a pi from G to gamma as follows. So I look at G hat, I look at X, and look at gamma. So since the vertex of G and G hat is the same, I can think of gamma both as a subset of G and G hat without doing anything. So that's the advantage. So first, what I do is I look at the cosine projection in G hat to gamma. So let me call this little pi. So let pi gamma of x be the closest point projection in G hat to gamma. Okay, very good. Then maybe I take like this is a Grove hyperbolic space. Maybe I take a delta neighborhood of that or something. Right. So then I define pi of x to be any point, so the union over all p's in delta neighborhood of this gamma projection of gamma intersect the D neighborhood of P. Right. So look at all possible P's that are nearby there. Taking them all to some D neighborhood. So that's N D of P. So yeah, pick this point, fathom this point in G hat, look at them in G, fathom them again in G, and then so maybe like this, you spin here and go away, and then you call this whole thing. Right, so extremely large set, as generous as possible, because any point in here is a reasonable projection. Like all these points are basically closest point to X in G hat. And I don't have a way of choosing which one of these is the best for X, right? So X is somewhere here, and I can go to any of these places equally well. So I just define this huge set to be the projection. So I'm going to now prove that this is, first of all, a kappa projection, and then I'm going to say that it's contracting. Recall the distance. Pi is a kappa projection. So this should be relatively obvious, hopefully. Right. So why? Because the subsegment of, so look at the first place, I don't know how to call this, let's call them Z and W, right? So this is gamma. Look at the first place and the last place in pi x. So that's Z and W in the first and last points in gamma intersect pi x. So gamma has a time parameter, so I can talk about the first and last. So then the dg hat of Z and W is some bounded number, right? Why? Because if you're pointing here, you are d close to some delta neighborhood of that. So your distance in G hat is at most d, if one step here is the same as moving in G hat, and then another is delta. So you're at most d plus delta. So the distance in G hat between these two guys is uniformly bounded, right? So the distance formula says that the diameter, so the distance between X and Z, or Z and W, is equal to, well, up to multiple error, the distance in G hat between Z and W plus sum of this P's, distance in P and Z and W. Okay, so if you pick any P that is not near here, the bounded image theorem tells you that the projection of Z and W is a small, right? So the only P's that can appear here are the P's that are visible here. So this guy is finite, you have to show. And then these guys are all less than kappa of norm Z of G hat. because the Z is the closest one to here. We can pick Z and W, doesn't matter. But the main thing is, so the Z, which is the point over here, since your Gromov hyperbolic is closer to origin than X, so these guys are less than kappa of G hat normal X. So I have some bounded number plus finitely many kappa numbers. So this is bounded by the kappa. The whole thing is bounded by some number C2 times kappa of normal X. So it is a kappa projection. So I don't know, this is too slow or too fast. I hope it's okay. But you see the basic thing, right? You have a distance formula, you have kappa excursion, means projection is done. Yeah, the proof of contracting is a little bit more involved. So I'll try to sketch a kind of an important statement. So I just want to state the correct fact here, and then try to justify the proof as much as possible. Right. So the kappa projection means a ball of radius r projects something bounded, right? The problem is the ball is of radius r in G, right? So, okay, so this is gamma. Let's set up the picture. Let's say you have a point X. This is distance r here, and you pick a ball much smaller, distance d1r. And you want to do this pi projection and say this is bounded, right? So, of course, the picture you have to have is that, well, this is in G. I should go to G hat. And then this ball becomes some ball, and this is hyperbolic, so projection is going to be bounded. Then I bring this back to G, and each of them become kappa, and I'm happy, right? So that's the proof, and that should be okay. The problem is, how do you know what this ball in G looks in G hat, right? How do you know it's really a ball? Like maybe it looks like some kind of elongated object like that. That the points X and Y in here in G hat are much farther than the distance over here, right? So this is the only thing to prove. So then what is the relation between a ball in G and a ball in G hat, right? So I have to say this picture does not help it. So that's the main theorem. So, and this theorem has been proven also in the mapping class group case. This is my work with maybe I'm not writing enough words here. The names, all of these talks, including the last two and this one, they are joint work with the Yulan Ching and Julia Tiosa. I was hoping this is clear from the beginning. So this is a sequence of papers that are joint with these authors. So yeah, all of these ideas and the papers are due to the joint work with Yulan and Julio. Okay, and this theorem also has precedent. There are various versions of it in the literature. Yeah, I mean, I think the ideas go back to Minsky, but okay. So what I want to say is exactly that. If I pick a ball, right? So it's distance between X and Y in G is less than or equal to some C times the distance between X and gamma. Okay. So there exists a constant C less than 1, such that this is true. If the distance between X and Y, so you pick 2 points X and Y, and this is much less than this distance, then the projection, this is the G projection. So do I have a name for that? I think so. Pi gamma of X and pi gamma of Y. Remember, these guys are in G hat. Is bounded uniform hat. So bounded distance in G implies the 2 points have bounded projection feature. Right, so yeah, I should just write one version of this was proven in the mapping class group in a joint work with Duchen, another version, yeah, so we use it in several other papers, but this is the most general version because it has all this kappa error terms and so on. So, and this was proven in the paper with Yulan and Julia. Not that this is a okay, so anyway, I hope everybody's happy. Just think about the whole thing. My claim is that to prove that I'm kappa contracting, all I need to prove is this theorem, right? That if I pick two points that are kind of close to each other in G, then they cannot project to points that are really far away in G hat. That cannot happen. Yeah, I was hoping to talk about the mapping class with it also. So I may be a tiny bit sketchy. So yeah, what is the proof? So let's do the contrapositive, of course, as usual. Assume this is big, and we want to prove the opposite of that. So imagine that you have X and Y whose projection in G hat is large, right? So assume the distance in G hat between pi gamma X and gamma Y is bigger than some very, very large number L. So what do I want to say? I want to examine the geodesic from here to here. So first of all, in G hat, this geodesic has to come really close to this guy's. So, I mean, how is it possible that the distance in G of XY is somehow much smaller than this distance? How could this be less than this distance? Remember, we have a distance formula. The distance between X and Y is sum of the distance in G hat and a bunch of peripheral distances. Right? So the distance in G hat of these two guys is definitely bigger than that because I have to come close to that, move along, go up here. So it can't be the G hat part. It has to be the peripheral. So I have to kind of examine each peripheral subgroup one at a time, right? So the G hat is hyperbolic, implies that the distance in G hat of X and Y is bigger than, but with some additive errors maybe, a distance in G hat of X and pi gamma of X. Okay, so now pick, okay, so this is good. Now pick a peripheral subgroup P. So where is this P? So somehow we have to have a P where it has a very small projection here, but a big projection here, but a small projection over there, right? Okay, so where is this P? The P cannot be here because bounded geodesic image theorem says that these guys will have bounded projection to here. So any P which could cause me problems has to be a P where these guys have big projection. So it has to be kind of near here, right? So for example, if the P is over here, okay, let's put it on this just to be suggestive. Then you can have this big projection here. But I want to say then these guys also have big projection because this guy also has to like do this exact thing, right? Okay, so let me write a few more words. So assume the distance in P of X and pi gamma of X is large, right? So means P is close to the geodesic connecting X, this pi gamma of X in G hat. Yeah. So if it's way up here, then the distance between these two guys is also going to be big because this is going to be small and this is going to be small, right? By the, yeah. Yeah, by the boundary mixture. So, but I don't want to do that up to here because, but near here there's kind of like messiness because if I have a P, it's possible that maybe P is close to that, but it's very big. Like the picture is somehow like to go from here to here. I have moved along this P, and then P is kind of like over here, and the geodesic kind of goes along this P, and then backtracks all the way from here and goes up. Okay, so all this nonsense could happen, but all these error terms are bounded by this kappa. So I still kind of win. So yeah, let me do this a little bit more. So I pick this point, auxiliary point Z, which is some like definite distance away from here, and is delta close to this particular geodesic, right? So if P is close to that, that means the distance in P between Z and pi gamma of Y is bounded, and distance in P between Z and pi gamma, between pi gamma of Y and Y is also bounded. Both of these guys are by bounded geodesic image theory. And then if you're kind of close to here, yeah, you have to say that you have to kind of deal with this separately and say that you're bounded by X only 10 or 2. Right. So if you're over here, like this whole thing is bounded. So you have to say the number of P's that can appear in between these two guys is bounded. Right? So if your P is up here, is not a problem, right? And in general, this part and this part is not a problem. So I have to kind of like discuss this distance compared with this distance and see how can this be much, much bigger than that, right? So I have to just analyze only finite many guys here. And so there are a bunch of kappa bounds that I get here. And okay, so let me just say the remaining peripheral subgroups, there are finite many, yeah. There are boundedly many peripheral subgroups remaining. Okay, so you do a bit more analysis. You win. Right. So, but yeah, that's kind of the basic thing is this kind of theorem follows from the hypervelocity of G plus the distance formula, right? If this distance is supposed to be big, means some peripheral subgroup has to be kind of big between here and here. But then the hypervelocity tells you that you're kind of doing that. So the same peripheral subgroup is still big from here to here, right? So basically I want to say this big implies this big, which is the same as saying this is a small and this is a small, and these are small by the bounded geodesic image theorem. Okay, that was a bit fast, but okay. Okay, so that's the end of my discussion about the relative hyperbolic groups. Right. So you have this projection, which is you use G hat to do the projection and then move them back to G. So this is the summary of it. These kind of projections are kind of wobbly, but the error terms can be bounded by kappa if gamma has kappa excursion. And then you have this theorem, which says that the small balls in G are still go to balls that are disjoint from gamma in G hat. So after, and this comes from the distance formula. And after you prove that, then you know that you're kappa contracting. So yeah, this being the key sentence. Okay, good. Yeah, let's talk about maybe actually let me opine a little bit about like I'm gonna like daydream a tiny bit about this sublinear Morse boundary and the relative hyperbolic groups. The relative hyperbolic groups already have a good boundary, which I consider to be the correct boundary and the direct analog of the Gromov hyperbolicity, the Gromov boundary for hyperbolic spaces. And this is called the Bowditch boundary, right? So if you, yeah, basically what you do is you look at all the rays going to infinity, but you collapse all peripheral subgroups into one point. So you're exactly doing what you would do. Just imagine you have a three-manifold, which doesn't have finite volume, but kind of like has infinite volume, right? With these tori things. And then if you look at that, this can become totally geodesic. And then they become kind of a bunch of copies of H2 sitting inside of H3. Like that, right? Maybe there's a red one, which also does something like that. And then the process of making this be relatively hyperbolic is like you collapse all these guys, right? So you have this whole part associated, maybe you cut these guys off because of the boundary, and you have a whole circle worth of boundary points for this. It's kind of like a Schottky group, right? The bound, and the boundary of this is some complement of all these disks, so some Menger curve or something. So it's a pretty carpet of some sort. And then you pick all these circles and you're collapsing them. And after you collapse them, you get this picture where this whole circle has turned into one point, right? And then the boundary, which was some crazy boundary, nicely becomes a S2. So this is the process that the Brian Bowditch does and produces this boundary called the Bowditch boundary. The Bowditch boundary is very nice, but it uses the underlying structural relative hyperbolic groups in it. So you look at these peripheral subgroups and collapse them kind of like as algebraic objects. But to me, you could detect maybe the non-hyperbolicity, right? So the question I have for everybody is, just imagine that the G is relatively hyperbolic with respect to these PIs, and imagine PIs are actually flats. Some ZNs or something, right? So it's not that they are peripheral in a sense of that you chose to kill these guys off. These are the actual flats, the only flats, and up to these flats, everything is hyperbolic, right? Then I should be able to build Bowditch boundary geometrically, like from the intrinsic geometry of the group, without knowing which peripheral subgroups are there or anything else like that, right? And what we're kind of showing is that the sublinear Morse boundary kind of like fits into the Bowditch boundary, hopefully in a very nice way. And Bowditch boundary has a property that is compact, right? So we should, so it kind of tells you that there has to be a compactification of the sublinear Morse boundary, where you just attach a point for all of these flats, right? So this would be a good direction for this to go to explore the relation between something that we already know that works and is very beautiful to what we have to, yeah. I mean, so basically I want a geometric construction of the Bowditch boundary, right? So that's what I'm hoping for. So nobody tells you who the PIs are, and this is the setup that you have, and then you build it, and hopefully the sublinear Morse boundary fits as a topological subspace, a dense topological subspace inside of that boundary. So that is the goal. It kind of like proves that this is if the algebraic and this geometric approach kind of meet perfectly in the middle, then that would be a very happy life for everybody. Okay, so that's all we want to say about that. So let's talk for like very briefly for the mountain class group. So yeah, so as Abdul mentioned, the mountain class group is hierarchically hyperbolic, right? So yeah, for people who don't know, this would be very short because I can't really explain what's going on. The mountain class group is a group of homeomorphisms of a surface. The main thing is you can understand is geometry of this mountain class group by the curve graph of various subsurfaces, right? So if I look at the curve complex of the surface, which is a space of curves connected by disjointness, right? So all these guys are Gromov hyperbolic. Okay. So there's an advantage here to the relatively hyperbolic groups, which is all the groups that you're choosing are hyperbolic at the same time. Their PIs didn't have to be. But there's a disadvantage here because like you could have this disjoint subsurfaces. So you don't have this bounded coastal penetration at all. You have actual product regions. So the two of this curved graph of here and here are disjoint and they could completely fail to each other all you want. But still there is this notion of a hierarchy path that we can look at the curve graph, we can look at the points X and Y, we can connect them together. So that's a sequence of curves. Let's call them alpha I. So for each of these alpha I, you can look at the surface S minus alpha I, which is also a surface, and you can try to connect this point to this point in that subsurface, in the curve graph of that subsurface. So you produce some picture like that, which is very similar to what we have. Like you have some underlying guideline from some hyperbolic space, which is a curve graph, and then in the complement you kind of do the same. But then here maybe you have a point beta I, beta j. So what you have to do is look at the surface Si minus alpha I minus beta j, and then you can do this again and again, and then you produce this wheel upon wheel picture, right? And these give you very nice quasi-geodesics called the hierarchy paths. So the distance formula here, dx and y, is going to be again like the distance in the curve graph of the main surface between x and y, plus sum of all other subsurfaces, distance in R of x and y. But you have to kind of cap this off for k. So this kind of similar formula works perfectly for the other guys. So you have this picture that you go to a particular subsurface, you do what you have to do in subsurface, and you go next. And again, the random walk things have this kappa excursion. So you can prove that you don't spend much time in any subsurface. So this is kind of a result of Sisto. So the kappa excursion property also holds. So the reason you get this P for the mapping class group is because if you analyze this, if you have a bunch of points in here, let's say bounded many points in here, and you know that all the excursions are bounded. So assume that the dr of xy is bounded by kappa norm of boundary of R in the curve graph. Right? So the distance from the origin to the boundary of the subsurface R. So if you plug that into this distance formula, you don't get that the length of this path. If this is bounded, right? So I'm imagining distance in the curve graph of x and y is bounded. So in the relative hyperbolic case, you would get that the distance between these guys are also bounded by kappa. But here you don't, because you have a bunch of wheels, finitely many of them. Each of them is length kappa, but each of those guys has their own wheels, which has length kappa. Each of them have their own wheels. So you have sequence of wheels upon wheels, and there's a whole bunch of surfaces inside their surfaces and so on. So the levels that you can go kind of is bounded by genus. So the conclusion you would get out of this is that the distance in the mapping class group between x and y is bounded by kappa to the power of some p. Let's say of normal x. So that's where the p comes from. Right, so the projection map that you have, even though excursions are kappa, the projection map is not kappa contracting; it's kappa to the power of p contracting. And if the kappa is small enough that this is sublinear, you're still good. And for the random walk purposes, the kappa is small enough; it's just log, and log to the power of p is still sublinear. So you still win. Yeah. So hopefully Julia will use this to prove that the sublinear Morse boundary is the Poisson boundary for both of these guys, the mapping class group and the relatively hyperbolic groups. Yeah, and the same proofs hopefully should work for which Abdul is doing for the HHG groups and so on. So you can generalize this to others. Okay, I hope this was useful. Thanks a lot for your attention. So just to advertise, the next week, what I'll do is I look at the other notions of genericity, which is the Patterson-Sullivan measure. So instead of random walk, there's other notion that you can think of, like how to put measure at infinity. And I want to prove that at least in some settings, the semi-Morse boundary is also generic with respect to that, not only random walk, but also the Patterson-Sullivan measure, right? So that's what we will do next. Okay, thanks. I'll stop.